Today we discuss intrinsic carrier concentration. The carrier concentration which is in thermal equilibrium condition, that is the steady state condition at given temperature without any external excitations such as light, pressure or electric field. At a given temperature, continuous thermal agitations result in the excitation of electrons from the valence band to the conduction band and leaves an equal number of holes in the valence band. An intrinsic semiconductor is one that contains relatively small amounts of impurities compared to the thermally generated electrons and holes. To obtain the electron density, that is the number of electrons per unit volume, in an intrinsic semiconductor, we first evaluate the electron density of an incremental energy range dE. The density Ne is given by the product of density of states Ne, that is the density of allowed energy states, including electron spin, per energy range per unit volume, and by the probability of occupying that energy range, that is given by Fe. Thus, the electron density in the conduction band is given by integrating these two equations. Uh, if we take for electrons, as we have shown over here, we have used the function GCE and the probability function is Fe dE, and for holes we have used GVE and we multiply it by 1 minus Fe dE. So the electron density in the conduction band is given by integrating these two from the top of the conduction band to the top of the, as we have shown in this integral, N0 is given by integrating 0 to E top, or we can say from the top of the conduction band EC to E top, GCE Fe dE. And equilibrium concentration of hole is given by P0 is equal to E bottom EV GVE 1 minus Fe dE. Here N is in centimeter cube and Ne is in centimeter cube electron volt to the power minus 1. The probability that an electron occupies an electronic state with energy E is given by the Fermi-Dirac distribution function, which is also called the Fermi distribution function, as we have shown in this equation in red. The Fermi distribution function Fe is given by 1 divided by 1 plus exponential E minus Ef by kT. Here K is the Boltzmann constant, T is the absolute temperature in degrees Kelvin, and EF is the energy in Fermi level. The Fermi energy is the energy at which the probability of occupation by an electron is exactly half. The Fermi distribution is illustrated in this figure. For different temperatures. We note that Fe is symmetrical around the Fermi energy EF. The energies that are 3 kT or below the Fermi energy, the exponential form of this equation becomes larger than 20 or smaller than 0.05 respectively. The Fermi distribution function can thus be approximated by simpler expressions. Fe is nearly equal to e to the power of minus E minus EF bracket closed divided by kT for E minus EF is greater than 3 kT and Fe is nearly equal to 1 minus e to the power of minus bracket E minus EF bracket closed divided by kT for E minus EF less than 3 kT. This equation can be regarded as probability that a hole occupies a state located in energy E. This figure shows schematically from left to right the band diagram, the density of states Ne, which varies as root E for given the electron effective mass, the Fermi distribution function, and the carrier concentration for an intrinsic semiconductor. The carrier concentration can be obtained graphically from equation which is given over here, and the product of Ne and GCE and GVE will give us the Ne versus E curve, which we have shown over here in these equations we have shown. The product of Ne and Fe gives the Ne versus E curve in this figure, the upper shaded area corresponds to the electron density. Here we have shown different equations and different diagrams. There are a large number of allowed states in the conduction band. However, for an intrinsic semiconductor, there will not be many electrons in the conduction band. However, the probability of an electron occupying one of these states is small. There are also a large number of allowed states in the valence band. By contrast, most of these occupied electrons. Thus, the probability of an electron occupying one of these states is the valence band is nearly unity. There will be only few unoccupied electron states, that is holes, in the valence band. We can see the Fermi level is located near the middle of the band gap. If we substitute the last equation, we get the equation as get n is equal to the electron concentration, which we can see is given by n0 is equal to nv e to the power e minus bracket ec minus ef by kt integral of e to the power ef minus en by kt. Here we can see that this nv and nc, they have got fixed values, and in our case this nv is given by 2 into 2 pi m f kt by h cross square to the power 3 by 2. The integral is in standard form, and it becomes n is equal to nc. Here we are seeing the product of n0 and p0, that becomes equal to na square, which is equal to nc into nv e to the power minus ev by kt. So this gives us na is equal to under root of nc nv e to the power minus ev by 2 kt. So we can see that P0 is equal to Ni e to the power of minus EF plus En by Kt. So this is the equation which we finally derive. For an intrinsic semiconductor, N is equal to P is equal to Ni. So Np is equal to Na square. Ni is the intrinsic carrier concentration. If we take the square root, this Ni is equal to N, which is equal to P, and that turns out to be Nc into Nv to the power half exponential of minus Eg by 2 kt, which is equal to 2 in brackets kt divided by 2 pi square h square bracket close to the power 3 by 2 me mh bracket close to the power 3 by 2 exponential of minus Eg divided by 2 kt bracket close. So this is the intrinsic carrier concentration in semiconductors. For intrinsic semiconductor, the number of electrons per unit volume in the conduction band is equal to the number of holes per unit volume in the valence band, that is n is equal to p is equal to ni, where ni is the intrinsic carrier density. The relationship of electrons and holes is depicted in figure which we have shown over here. Here, the Fermi level for an intrinsic semiconductor is obtained, which gives us EF is equal to EI is equal to EC plus EV divided by 2 plus in brackets KT by 2 bracket close ln NV by NC. At room temperature, the second term is much smaller than the band gap. Hence, the intrinsic Fermi level EI of intrinsic semiconductor generally lies or close to the middle of the band gap. The intrinsic carrier density is obtained as Np is equal to Ni square, and Ni square is equal to Nc Nv exponential bracket minus Eg by Kt bracket close. So Ni is equal to under root of Nc Nv exponential minus Eg by 2 Kt. After this we have a curve which shows the temperature dependence of the intrinsic carrier concentration Ni for silicon, gallium arsenide and germanium. At room temperature, that is at around 300 Kelvin, Ni is of the order of 9.65 into 10 power of 9 per centimeter cube for silicon and 2.25 into 10 power 6 centimeter cube for gallium arsenide. The larger the band gap, the smaller the intrinsic carrier density. Thank you.